decided that max-min problems are so important, and it was probably pretty hard to concentrate on 5 problems in one shot, I decided to break this into 2 videos. So we just have 2 more max-min problems to do today. So the first one involves you wanting to make a garden that has 1,000 square feet of area, and you have a landscape architect who told you that it would be nice to have one side brick and the other 3 sides wood. So brick costs $30 per foot and wood costs $10 per foot. So you want to meet all your requirements at the minimum cost. So probably be a good idea to make a little picture of your garden. You could put the brick on this side. And what are the dimensions in your garden? 2 dimensions, X and Y. And what we're trying to do is minimize cost. So our dependent variable probably could be C, and it depends on the 2 dimensions that you pick. So it costs $30 per foot times the number of feet of brick, which is X, plus $10 per foot times the number of feet of wood, which is 1Y, 2 Ys, and 1X. And just to simplify things, you can put all the X's together. Altogether you get 40X plus 20Y. And we've got a nice function. Unfortunately, like it's happened before, we've got 2 independent variables. So we have to get it down to just 1. And you can go back to your picture and know that we need 1,000 square feet. So we know that X times Y has to equal 1,000, or Y equals 1,000 over X. So we have a relationship that I can replace my Y with 1,000 over X. So we have 40X plus 20 times 1,000 over X. Or altogether you have 40X plus 20,000 over X. Well, we're going to have to take a derivative of it, so maybe we'll call it X to the negative first power. Now it's just a function of one independent variable X, and C is the dependent variable. So we're going to take a derivative like we always do, and we get 40 minus 20,000 X to the negative 2. So I can make that over X squared, and I want to see where that's 0 or undefined, looking for critical values. Well, you can't divide by 0, but I think we should get a domain for this. What do we know about X? You can't have negative amount of fencing, and you really can't have 0 and still have a garden. So I think X has to be greater than 0, and you probably don't want X to be like 1,000,000 feet, but there's nothing really restricting you from doing that. You could still make Y really, really small and still meet your requirements. We'll let the math take care of that. So we'll just say that X has to be greater than 0. Well, that puts dividing by 0 out of possibilities in our domain. So I don't have to worry about undefined. But where is it equal to 0? Well, if I do a little bit of algebra, I get 40 equals 20,000 over X squared, or X squared equals 500, or X equals the square root of 500, which contains a perfect square. 10 times 10 is 100, so this is 10 times root 5. Now we know what X is, and from our relationship over here, we can say Y is 1,000 over 10 root 5. One of the zeros cancel. And if you rationalize your denominator, you have 100 root 5 over 5, or 20 root 5. Now, we haven't really checked to see whether that's a max or a min, so we probably should put it on our number line like we usually do. And all we know is that x has to be greater than 0, and it can be as big as it wants. And that was our only critical value. Well, if you take a number less than this, like 1, the derivative would be 40 minus 20,000, which is pretty negative. And if you took a really big value of x greater than 10 root 5, this gets really small, so the derivative is positive. So you can see that the cost goes down and then it goes up. So this really is not only a local minimum, but an absolute minimum. You can see that the cost goes higher in both directions. So we've pretty much got our answer. We're going to build our garden to be 10 root 5 on this side and 20 root 5 on this side. A little bit different than the shape that I've got. We use less brick. The side that's brick is smaller. So we still haven't quite answered the question, what is the total cost? Well, we can come back to here and say the cost is going to be 40x, so 40 times 10 root 5 plus 20y, and y was 20 root 5. So altogether you get 400 root 5 plus 400 root 5, or 800 times the square root of 5. And if you put that on your calculator, it's approximately $1,788. And we solved something that's pretty important and helpful to us. Now I have a part B. It says, say for cosmetic reasons, the landscape architect said you really should have your brick wall between 10 and 20 feet. Well, we don't have to redo all this calculation. Everything is still the same. All our relationships are the same. The only thing that's really changed is this domain. No longer does x have to just be greater than 0. X has to be between 10 and 20, because that's the amount of brick. So all we really have to do is rechange the domain, and we see, since 10 times the square root of 5 is bigger than 20, it's going to be over here. And we know that until you get to 10 root 5, the cost, or the derivative of the cost, was always negative. So in this whole area that we're looking at, the whole domain, the derivative is always decreasing. So the cost is always going to be coming down. So that means the best thing to do would make x be 20. And if x is 20, then y is going to be 1,000 divided by 20, or 50. So you're not going to be these dimensions, you're going to be 20 by 50. And then your cost is going to be 40 times 20 plus 20 times 50. And altogether that's $1,800. So if you had that restriction, it's going to cost you a little bit more. But if it's going to look a little bit nicer, maybe that would be the best thing to do. Okay, so let's look at one last problem. Michael is in a rowboat 2 miles from the nearest point on a straight shoreline. So I'm going to just draw that so far. Here's a straight shoreline. Michael is out here in the water, and he's 2 feet from shoreline. So I'm going to label this to be 2. what else do we know? His house is 6 miles down the shoreline from this point. So here's his house right here. And we know how fast he rows, 6 miles per hour, and he runs a little bit faster at 10 miles per hour. It says, how should he proceed to get to his house in minimum amount of time? Well, he has his choices. He could row straight to shore and then run the rest of the way. He could row straight to his house in the shortest distance he could do, and that's probably the decision he would make if he rowed faster than he ran. But since he runs faster than he rows, maybe that's not the best decision. So the key is he could either go to here or anywhere in between. So we're going to let the math make the decision. We're going to let calculus decide for us. So we're going to call the one decision we have is where to make this point. So I'm going to call x the distance from here to here. And then we know this distance is going to be 6 minus x, because the total distance is 6. And then we should put in here the distance that he rows. Well, you could call it another variable like y, but you're going to have to get down to only one independent variable anyway. So maybe right away we should look for a relationship that doesn't need another variable. Well, we've got Pythagorean's theorem. So this side, x squared plus this side squared, you take the square root of it, and the hypotenuse is going to be the square root of x squared plus 4. So now we're going to minimize time. And it's only going to depend on x. Now you have to think back. Distance equals rate times time. So time equals distance divided by the rate that you're running or rowing. So let's do the rowing first. That's the distance that you row, and you row at 6 miles per hour. That's the rate. Now for the running, the distance you run is 6 minus x, and the rate is 10. So we've got our function. And it only has one independent variable. As far as the domain is concerned, x could be a negative number. You could pick x to be over here. It would be a pretty stupid decision to row away from your house. And I think x probably has to be less than or equal to 6, because I don't think you would row past your house. So you could put a domain like this, or you could just say, we'll let the math take care of things. I think you're going to find out that the answer is the same in both cases. So if you feel more comfortable with this, fine. If not, we'll just assume x could be any real number. So now it comes down to taking the derivative, like we always do. But before we take the derivative, let's make it a little bit easier for us. Call this 1/6 times x squared plus 4 to the 1/2 power. And call this just 1/10 times 6 minus x. So now when I take the derivative, what do I get? 1/2 times 1/6 is 1/12 times x squared plus 4 to the negative 1/2. And then times the derivative of this, we've got to do the chain rule, is 2x. And the derivative of 6 minus x is just negative 1. We want to look for critical values, so we set that equal to 0 or undefined. So we have a little bit of algebra to do here. I think it's never going to be undefined because this is always positive in here. The square root is never going to be negative or 0. So we have no real problems there. But if I rewrite this, I get x over 6 times the square root of x squared plus 4 minus 1/10 equals 0. So if I set that equal to 1 over 10, that's the relationship that we have to solve for. So if I cross multiply, I get 10x equals 6 times the square root of x squared plus 4. To get rid of that radical sign, I probably should square both sides. So you get 100 x squared equals 36 times x squared plus 4. Or altogether, if you distribute through, you get 64x squared equals 144. Or x squared equals 144 over 64. And if you take the square root, you get 12 over 8, or 1.5. And the last thing we have to do to make sure we're not maximizing the time is put that on the number line. And you can either put 0 to 6 or you can put the whole real number line. And if I put 1.5 right here, and put that into my derivative right here, I can see when I get a really small, if you look at it this way, if I get a really small value of x, like 0, I get 0 minus 1/10 would be negative. But as x gets really large, like 6, then I get 1/2 minus 1/10, which is positive. So I can see that the absolute and local minimum is going to be when t equals 3/2. So it really doesn't matter whether I had the 0 to 6 on here or not, I still come up with the same answer. And I know exactly what, Michael knows exactly what he should do. He should not aim to the closest place. He should not aim over here. He should aim 1.5 miles from the closest point on shore. So anyway, I think we've solved his problem. And I think these two problems are really pretty tough problems. So if you can do these, you can just do most any max-min problems. So I think we've pretty much had it for today. I know I probably shouldn't do this to you, but what should Michael do now that he really figured out his best way to proceed? Michael rowed the boat ashore, hallelujah. Michael rowed the boat ashore, hallelujah. So have a good day. Sorry I did that to you.